Okay, so this is the new schedule. This is the talk tomorrow. Those are the questions you answered. And here's what we're doing today. Matrix algebra. And the most important thing in what we'll talk about today is that it's exact matrix algebra. So going to this kind of outline of what we're doing today, I've posted a PDF of the log of the session that we're about to see, and also a Sage worksheet. The PDF, you can just click on it and you'll see the session. And if you look, there it is. So that's what we'll do today. One thing, some people pointed out to me, that's a big answer, that in some cases the input is a little bit missing. And the bug in Sage that caused some of the input to get broken, to get kind of truncated off, has been fixed. So that's not an issue anymore. So the PDF doesn't miss little bits. You can also download the Sage worksheet to your computer and then upload it into a copy of Sage and just start using it, and then kind of do exactly what I did here. By the way, big news, Sage 3.0 has been released. If you go to sagemath.org, there's a note right at the beginning that Sage 3.0 has been released. Is this your homework?
Yeah.
So, who wants to trade here? Cameron. All right, trade is done. Here you are. Okay, so Sage 3.0 has been released. That means that if you've installed Sage, you may want to download a new version and install it. If you really, really are brave, you can try the upgrade command. But the main recommendation is to either install again from source or to download one of the binaries. So for example, for Mac OS 10, you can download one of these binaries. Okay, so there are lots of binaries posted. It's a pretty significant release, as the number should suggest. This discusses, so there are 48 people who during the last 3 weeks contributed to this new release, and those people are listed here. And this is a list of some of the major new features. Random numbers have been very systematically organized in Sage so that there's a single random number seed that initializes the random numbers for everything in Sage. The person who implemented that is this guy right here, who's in IRC right now, C. Woody. Michael Abshoff made it so that GCC 4.3 supports their, we have more binaries than we had before. Like we're building binaries for Itanium by default. Does anybody here have an Itanium? Has anybody here heard of an Itanium? It's just an architecture that Intel thought would be the next big thing. 10 years ago, or 5 years ago. It wasn't. But some people bought them. So. And then there's some other things. The reason I started Sage in the beginning was to create a package for computing with modular abelian varieties, and we now have such a thing, finally. We have way, way, way more examples. Overall, the coverage went up in the last 2 months from about 32 or 33% of the functions having examples to 51.5%. So it's a great increase. We have a much nicer interface to R and some other things. And there's a kind of a release tour if you want to see more details about some of these things right here. Which it has examples and that sort of thing. So Sage 3.0 is out, and you can get it now for the low, low price of nothing. All right, so now on to exact linear algebra. So, oh, by the way, you asked me why everything goes so quickly when I'm using the Sage notebook right here in front of you. And the reason is because I'm running Sage locally on my laptop. If you go to sagenv.org, your mileage may vary regarding speed. Or it might not work at all because you're using Firefox 3, which you have to add an exception to allow that. Confirm security exception. Because I haven't yet jumped through all the hoops to have an official SSL certificate. But the speed can be slow. There are various reasons for this that people are working on fixing, but the Sage notebook has several thousand accounts, and there's just a lot of information there that is not stored in a very good way. Thanks, Ross. This is the Sage IRC channel, which has all of these people logged into it right now, as you can see. If you're in class and you're logged in, raise your hand. Just you. I'm teaching. Okay, so you should know, well, you can see it's slow. Sometimes it will take a minute or two, and then you'll get a nice connection for a while, and then it'll get slow again. If you install Sage on your own computer, which you can do for Linux, OS X, Windows, all three are supported, then it's much, much faster, as you can see here. The public Sage notebook, I think, would be a lot faster if one of you would do a project, which is just about maintaining the server. That would require rewriting some of the backend stuff so that it uses a database instead of a very, very simplistic storage format. And also just, say, spending an hour or two each week working on it. It would be a really good job to have. But I just don't have time to spend a lot of time making that public thing very fast. Are we teaching now? Trying to illustrate that Sage is a living project. No swearing. Okay, so on to our presentation. So this guy right here, actually, M. Hampton, he was a UW grad student a couple of years ago, right, Jim? Yeah, or he was a UW student for quite a while, and he's in Texas right now giving some talks on Sage. I think Texas A&M. All right. Okay, so the three kind of main. Okay, this could get distracting. Okay, so the three main points I want to make today are that, so exact linear algebra. So how many people here have taken some sort of linear algebra course? So everybody. So you probably put a matrix in reduced row echelon form, you computed the null space and the rank, you found a few characteristic polynomials, you found eigenvalues, you did all that kind of stuff, right? And whenever you did it by hand in exercises, you pretty much always started with a matrix like this. That has nice entries, and you did some arithmetic, and it either got really nasty or it stayed pretty nice. And very often, if it was kind of a pure math linear algebra class, you ended up with lots of rational numbers as you went, if you did calculations by hand. Does that sound familiar to anybody? Like really, really familiar. On the other hand, if you took a class involving linear algebra from a more numerical context, then the numbers are floating point numbers, and there are lots and lots of flashing red signs about if you do exactly what you did in the pure math class, you may end up with answers that don't quite make sense because of numerical stability issues and so on. Those issues, numerical stability in the context of exact linear algebra, by which I mean linear algebra with rational numbers, or integers, or elements of a finite field, or polynomials over, or rational functions over those rings, there you don't have any issues with overflow, or round off, or whatever. So it's linear algebra over integers, rationals, finite fields, G of Q, polynomial, rational functions, that sort of thing. So here you don't have round off error. You do have a big problem though. Which is when you actually try to do calculations, if you use really any of the algorithms that you learned about in your in a standard class in linear algebra, the numbers that are involved can get really big as you go. For example, if you imagine taking, say, a completely random 50 by 50 matrix and then putting it in reduced row echelon form. First, you're probably going to end up with the identity matrix, unless the matrix doesn't have full rank. A random matrix is going to have full rank. So at the end of the day, you're going to end up with the identity matrix. But imagine what would happen along the way if you're just following the standard algorithm. I mean, the numbers are going to get huge. You'll take the first entry and you'll clear this column. And these numbers are going to get consequently really big. And you'll do the same thing with the first entry in this second row and third row, and then when you get down to the 20th row, the numbers over here are going to be absolutely crazy gigantic. So you have to watch out for that and try to find algorithms, or do exist algorithms that avoid this coefficient explosion problem. But this is one of the main things that kind of replaces numerical stability problems in the context of numerical linear algebra. So we don't have this, but we do have that in the context of exact linear algebra. Another issue with exact linear algebra is that basically to an extremely large extent, the only people who get paid to work full-time on exact linear algebra are cryptographers. And cryptographers are not very open about what they do by their nature. So if you think about numerical linear algebra, there's a vast number of people who literally get paid full-time to do things related to numerical linear algebra. Because it's sort of a basic building block in doing a huge amount of scientific computing. So there's all kinds of libraries, the situation is essentially extremely good for numerical linear algebra. On the other hand, for exact linear algebra, the situation is really good for these groups of cryptographers, say, but it's not nearly on the same level as numerical linear algebra, as far as just the situation being really good. There's one group that has got paid full-time to work on exact linear algebra for quite a long time, and that's the Magma developers. And consequently, Magma has extraordinarily good exact linear algebra. So it's very good at this game in the situation of dense matrices. So very good at exact linear algebra. And when you're doing algebraic computation, there are basically a couple of building blocks that are very, very important. So there's polynomial factorization, polynomial multiplication, basic arithmetic with integers, and there's exact linear algebra. And there really isn't that much more. A lot of stuff just boils down to operations with matrices like matrix multiplication, reduced row echelon form, computation of characteristic polynomials, that sort of thing. And Magma, there's really a large amount of things that have been built on top of these basic building blocks, and these basic building blocks have been just optimized to death in Magma. And likewise in Sage, we've also done a huge amount of work optimizing exact linear algebra. And in many cases, Sage is now a little bit faster than Magma at exact linear algebra operations. In other cases, Magma is substantially faster. It's really a mix. But the one important thing to take away, I'm not going to show you a bunch of benchmarks, but Maple and Mathematica and MATLAB, none of those programs are any good at exact linear algebra when you get into large problems. And it's kind of surprising how bad they are, actually. There are also systems like Perry and Gap, which are kind of serviceable at exact linear algebra when the problems are small, where small means up to 100 by 100 matrices, that sort of size. The interesting thing with exact linear algebra is that there are actually a whole bunch of very surprising algorithms that are asymptotically fast. They're asymptotically better than the obvious algorithms. So one very, very famous example of this is matrix multiplication. There's a method that started with a paper of Strawson, where what he did was he proved that you can multiply two matrices where the number of the number of multiplications actually is less than O of n cubed. So imagine that you have two matrices that are both n by n. So this is a big matrix. There's another big matrix. And say each matrix, just to fix ideas, has n rows and n columns. So if you think about the algorithm that you know from a linear algebra class to multiply these two matrices, let's just count up how many times we do a multiplication. So you take the first row, and you take each entry in that row and multiply it by the corresponding entries in the first column. How many multiplications do you do? N, that's right. And now you're going to do exactly that for every single entry in the output. So how many multiplications do you do? So you do n squared, n multiplies, which is n cubed multiplies. So the complexity of that is O of n cubed. Well, in fact, it multiplies in your base fields exactly n cubed multiplies. Now the funny thing that Strawson observed was, just for starters, in a special case when you can break the matrix up into submatrices that are half as big, so let's assume n is even for a moment. Then what he did was he wrote down an explicit formula for multiplying two 2x2 matrices that takes only 7 multiplies instead of 8. What you do is you just view these big matrices as, you view the big n by n matrix as a 2x2 matrix over smaller matrices. And then you use Strawson's explicit formula to do this matrix multiplication, and you end up doing only 7 matrix multiplies, which is kind of surprising. So somehow you do a little bit less. You do more additions, but you do 7 multiplies instead of 8. The obvious thing to do would be to just multiply the blocks. That gives you 8 multiplies. That's no good. And then the really funny thing is, on each of the submatrices, when you multiply them, you again use the same recursive decomposition. And you end up getting an algorithm that, instead of taking O of n cubed steps, takes O of log base 2 of 7 steps. And log base 2 of 7 is less than 3. So the number of arithmetic operations that are multiplies are smaller if you use Strawson's algorithm. But there's a huge amount of overhead in implementing Strawson's algorithm, just kind of a ridiculous amount of overhead. So it turns out that for small matrices, it's still better to do this. However, as the matrices get larger and larger, and you get better and better at implementing this algorithm, and you start taking into account things like cache misses, and get better and better at implementing your algorithm in such a way that it's cache-friendly, so to speak, then this starts taking over. And that's just one illustration, but with matrix multiplication, where for larger and larger n, say n around 100 or 500, using an algorithm like this can make a big difference. Think about it. There's a big difference between n cubed and n to the power of 2.7. Let's look at an example. Let's say 500 cubed, numerically, and 500 to the power of log base 2, that's right, base 2. Yeah, look at that. Maybe I won't put I mean, it's way better actually. Maybe I'll put it as a factor. There's the 7 instead of the 8 at the end. So let's see how much better it is. Look at that, 3.3 times. So let's say that just by changing your algorithm, you could have something be over 3 times faster already for a 500 by 500 matrix. So that could be the difference between 1 hour and 20 minutes. And taking into account various issues involving caching and so on, it can end up being even more of a factor. But just naively, the number of multiplies you do is like this. And when you start doing serious math, you can easily start wondering about things that happen with 2,000 by 2,000 matrices. Let's see what the correspondence is there. And by the way, most of linear algebra you can reduce to matrix multiplication. A huge amount of it reduces. For example, the question of computing the echelon form of a matrix. You can rephrase that as a matrix multiplication question. It's very surprising, but it is possible to encode that in matrix multiplication. So for 2,000 by 2,000, you see a factor of 4 here. So that's pretty good. And there are also some slight refinements on this, but seeing this sort of speed up just by changing your algorithm can really matter. 10 minutes versus 45 minutes. Big difference. Yes?
Aren't there algorithms that can get down to like 2 to the 2.3 or something?
Theoretically, yes. There is an algorithm, Strawson-Vinograd, that has a better exponent than log base 2 of 7, but people don't implement it because there's a constant involving the complexity of implementing the thing and other factors. Yeah. And it will be better for sufficiently large sizes of your matrices, but sufficiently large may be huge. Also one really, really surprising thing that you might not think of. So let's say you want to multiply 2 matrices, and they have integer entries, and you want an integer matrix out. Okay? If you, the first thing you might do is try it in, say, some program, and notice it's pretty slow compared to, say, Mathematica, which can multiply, sorry, not Mathematica, MATLAB, which can multiply very, very quickly because it does everything with floating point numbers. Or Sage using floating point numbers. I mean, they're about the same. So you might go, oh my god, that's really annoying. I really, really wish I could do the multiply with floating point numbers. But of course, your answer could just be completely wrong because the numbers overflow. I mean, let's just take a simple example like that. I'll make a random matrix over the integers that's, say, I don't know, not even very big, 100 by 100. And I'm going to make the entries be about maybe positive numbers between 0 and 10 to the 5th. Okay? And now I'm going to square that matrix. Any idea how big the entries are going to be? I mean, you can estimate it pretty easily. Just think about doing the multiplication directly. You have 10 digits. Each time you multiply two of these numbers, you get 10 digits. You add up 100 of them. So it's going to be like 11 digits. It's not too bad, actually. So there's the first row. So if you were to do that numerically, you'd probably get some overflow. Here it's not too bad yet, but if we did the same thing numerically, I'm just going to square this numerically to see what I get. Same matrix, and I get this, and that's fine, actually. So that works fine. So in some cases, you can do it, but then let's say instead of the numbers being up to 10 to the 5th, they're up to 10 to the 7th. Now let's look at that. Same problem, but the numbers are a little bit bigger. And then when you try to do it numerically, pow, just doesn't fit in the precision of your matrix multiplication. You get most of the digits, but you lose off the last few digits. So it gets very frustrating. You wonder, isn't there some way? Is there some clever trick that allows you to do this anyways? And the answer is yes. What you do is instead of multiplying really big matrices, you do a couple of things. First, you do the multiply by multiplying modulo several different primes, and then using the Chinese remainder theorem. So that's the first trick. Then the second trick is you can do matrix multiplication mod primes using this algorithm where you recursively decompose, and you end up only ever actually multiplying matrices mod primes where the matrices aren't very big. Say you're working mod, say, a prime that's around 40,000, for example, and you only ever multiply 100 by 100 matrices. That exactly puts you back in the situation where you can do the multiplication using floating point arithmetic and not overflow. So you do that, then use the Chinese remainder theorem, and you end up getting the original thing. And by doing that, you get extremely fast matrix multiplication. That's actually the best way for people to multiply matrices with integer entries when they get large. And the funny thing is, behind the scenes, you end up actually multiplying tons of matrices with numerical entries, with floating point entries. So all these scientists and whatever who have optimized the heck out of numerical matrix multiplication and so on, because of Straussen's recursive decomposition and the Chinese remainder theorem, their work directly benefits the speed of matrix multiplication over the integers, which is kind of cool. And actually, the first person to write a paper kind of examining all this this algorithm I just described systematically and dealing with, I mean, it's pretty obvious what the algorithm is when I describe it, but there's very subtle issues involving caching and how do you implement it to really work well and so on. And it's surprising that it often does work so well. The guy who wrote the first paper about this is Clement Pernet, who's a postdoc here. And he'll be teaching, hopefully, a grad course next quarter on exact linear algebra. So if you're around next quarter, you may want to take his class or audit it. Okay, let's see, any other points? Nope. Okay, so now I'm just going to give you a kind of brief tour in the remaining moments of how to actually do some things with linear algebra in Sage and matrices. So one thing is I'm certainly not going to be able to show you everything, so you're going to want to look at the worksheet that's posted. So here's how you make a matrix. It used to be that, it used to be the only way to make a matrix in Sage was to make a matrix space. So this is kind of like making a ring. You make the collection of, the set of all matrices whose entries are in a given ring, say the rational numbers, of that size, and then you can make a matrix in there. But this undergrad who was working for me, who was a physics major, Alex Clemenshaw, he just thought that was the most ridiculous thing imaginable. So he strongly lobbied that there just be a really, really straightforward to use matrix command, and now there is. And this matrix command is extremely powerful and flexible. All you do is you give it the number of rows and columns and the entries of the matrix. That's it. It has various options, like you can specify I want every single entry to be in the real double field. And what it will do is it will push them all to be in the real double field, irregardless of where they are before you start. One thing with matrices in Sage, once a matrix is created, all the entries all lie in the same ring. So if any one of them is a complex number, they're all going to be complex numbers. If any one of them, and the complex numbers if every number can be made sense of as a complex number, and at least one of them is, it's pretty likely they all will be. That's not a precise enough statement. What internally happens is when you try to make a matrix, if you explicitly specify where you want all the entries to live as the first argument, then it tries to make every entry into an entry in there, and if it fails, it gives you an error message. For example, if we stuck, say, the indeterminate x right here, it's just going to give us an error message. How? You can't do that. So you can't do that. But if we, the other thing is if you don't specify the ring, it tries to automatically figure it out. So here's an example where we'll make one entry be pi. And now it looks like they're all rationals, but they're really symbolic objects. Or we can make one of the entries be g. How about the number 1 modulo 11? Okay. It cannot do that because it's not. There's no canonical way to do that. Let's see. How about the complex double field? Wait. Oh, wait. Sorry. That doesn't make sense. Make one in the complex double field. There's every single entry gets put there. What it does is some funny algorithm where it tries to put them all canonically in one single ring. And if it can, then it says yes, and it gives you back that. And if it can't, it gives you an error message, like it did. Well, actually, I didn't give you any examples where it gave an error message. Actually, it did with the GF. Yes?
Will the type command tell you what ring it's dealing with?
Yes. If you want to find out what ring it ended up putting the thing in, you can. Actually, type won't. So if you say type, it tells you it's a well, it'll give you some information, but it's not the best. This tells you it's a matrix complex double dense matrix. That does, in fact, tell you what you wanted to know, but really the best thing to do is just to call the base ring function. That will tell you literally the ring that the matrix was created in. Yes, Robert?
For anything, you can call a parent.
Yes, that's another thing you can do. That'll give the matrix space. So if you go a dot parent, you get the collection of all matrices over that field. So this is shockingly different than how matrices are treated in Mathematica, for example, but somewhat similar to how they are in MATLAB. In Mathematica, you can make a matrix which has one entry that's a half, another entry is a polynomial, a third entry is a picture, a fourth entry is your email address, whatever, and it'll try to do stuff with it. In Sage, matrices are completely homogeneous. Every entry has the same type. That's probably one of the most important things that's different between Sage and these other systems. The advantage of this is that a lot of linear algebra can be much, much faster because when Sage does an operation like matrix multiplication or compute the characteristic polynomial or the determinant or whatever, it instantly knows that every single entry in the matrix has this one type, and then it will use an appropriate algorithm that's designed specifically for that type of element, for that ring. Whereas in other systems, what happens often is either there's a command, say char poly, and it uses one single algorithm that works for every possible ring, which sounds really beautiful in the abstract, but in practice, the result can often be extraordinarily slow. Or what you end up doing is you have to hunt through lots of documentation, and you'll find that there's a special command that does a calculation on your matrix, assuming that the ring is a certain ring, and fails if it isn't. But in Sage, you don't have to worry about that at all. Also, if there are special commands that are available for a given base ring, like if you make a matrix over the integers using, say, the random matrix command, which is a handy command for making up examples of matrices, I just made a matrix with integer entries. I could do a.tab, and I'll see that there's a lot of different functionality available. This is everything. But there's also some functionality that's special to the integers. For example, there's something called the Hermite form, which is something that only makes sense for the integers. It's the analog of the reduced for echelon form over the integers. And I'll show you what it looks like. There it is. So this is like putting that matrix up here in reduced row echelon form, but over the integers. And when you did tab completion, you'd only see the Hermite form algorithm if your matrix has integer entries. So that's like a key thing to remember about how matrices work in Sage. The key thing, again, being that all the entries are in the same ring, the same sort of place. It's kind of like, I think, in a calculator or in MATLAB where you set the number of digits of working precision. The ring is like choosing that number of digits of precision. In fact, some of the rings are just numerical entries with a given amount of precision. It's just that you can have a whole bunch of different rings all at the same time, which is nice. There's also support for sparse matrices. Here I just made a 1,000,000 by 1,000,000 matrix. And it took no time at all, and it didn't run out of memory. But literally, this is a 1,000,000 by 1,000,000 sparse matrix. And I set one of the entries, it's the sparse 0 matrix. I set one of the entries to be -4/5, and there it is. So you can see that one in tree. Is that. And there is an optimized type specifically for sparse linear algebra over the rational numbers, since that's something that's very important for my research, for example. Okay, moving on. Here's an example of doing matrix multiplication. It's not too hard to remember how to do matrix multiplication. You just use the star, just multiply. You might think that's the most obvious thing imaginable, but NumPy, which is a numerical linear algebra package included in Sage, written by a lot of scientific computing people, you make two matrices there and then multiply them. It multiplies the entries component-wise, which is very confusing. In fact, it's usually a lot of work to figure out how to do this meaning of matrix multiplication. So you kind of have to watch out sometimes with other packages. But with Sage itself, with any matrix multiplication, it's just multiplication. There's also a very handy backslash operator, which is exactly like in MATLAB. It's the solve operator. So what this does, and it works in a huge amount of generality. It even works if the matrix A is singular. A does not have to be a square matrix. A does not have to have full rank, etc. It works in the, it works when B can be a vector or a matrix, whatever. And it works over in kind of any context. So just because that's such an important command to know about, I'm just going to write it right here. So if you write A backslash B, or if x equals A backslash B, then AX equals B. So you solve AX equal to B by writing this right here. Okay? And B can be a matrix or a vector, and A can be a matrix of any size, singular, non-singular, whatever. And actually, that's a pretty recent addition to Sage that A can be anything, instead of having to be a square non-singular matrix. But again, we needed that very much for this modular dealing varieties package that I mentioned at the beginning of class, and so I implemented it. It's kind of funny because literally, right when I was in the middle of implementing it, somebody popped up in IRC and asked for exactly that function for his research. So I was happy to get him to read all the source code and make sure it was right, since he immediately had to use it. So he was forced to be the referee for the code. Let's see. Here's some examples of just good old-fashioned reduced to echelon form. The command is not hard to remember. It's just echelon form. So you can create a matrix, and then if you don't remember anything, just do .tab, and you'll see echelon there, and then there it is. And of course, if you want to get examples and so on, you, as usual, do this, and you'll see some examples. And there, over the rational numbers, there's actually a lot of interesting algorithms for computing the reduced to echelon form, some of which are very clever. Actually, I guess there's a grand total of 2, but that's a lot, because both of them are pretty interesting. There's actually a third that we haven't implemented that isn't listed here. But I'm not sure what I want to say. So the multi-modular algorithm, what you do is you want to compute the reduced to echelon form of a matrix with rational number entries. Here's an idea. You take the matrix, has all these big entries in it or whatever, you reduce every single entry modulo a prime p, modulo 389. You just reduce all the numbers modulo 389. And then you do the entire echelon form just in a completely naive way, say modulo 389. So there's no coefficient explosion, you're always reducing mod 389, things don't get out of hand, and you get the reduced to echelon form modulo 389. Now you do exactly the same thing about another prime, and another prime, and another prime. Then you use the Chinese remainder theorem to combine all the answers together, and then you get something in characteristic 0. And that doesn't work at all. When you use the Chinese remainder theorem to combine the answers together, you end up getting a matrix with integer entries. However, look at any example of a matrix that you've computed the reduced to echelon form of. It does not have integer entries. It has these terrifying large entries that are rational numbers typically. That's just what happens. However, it turns out that there's a really neat idea that's, for example, described nicely in volume 2 of Knut's book called rational reconstruction, which allows you to take a matrix modulo a large integer and find, subject to certain conditions, the unique matrix over the rationals that reduces to that matrix. So again, that's called rational reconstruction. And it's really just a generalization of, let's take, say, the rational number 5/7 modulo, I don't know, this big number, which I hope is coprime to 7. And I'll just show you. It seems like magic, but it just involves the Euclidean algorithm. So 5/7 modulo that big number is this number. Now watch this. If I take that number and this number, pow, isn't that cool? It tells you that 5/7 is the right rational number that reduced to get this. So the algorithm implements this again. It basically just looks like the Euclidean algorithm, like the GCD algorithm, where you keep subtracting and dividing. But at a certain step, you check a certain condition, and you can read off from what the information you get from the GCD algorithm. Either there exists a unique rational number whose numerator and denominator is at most, I think, 2 times the square root of this, or there's no such number. You get to determine yes or no. And it's actually, it's pretty subtle though. I think the first 1 or 2 papers about this had mistakes, and I mean, there's all kinds of little subtle things in the edge cases. But there's a nice algorithm for doing this. So that's one algorithm. There's also an algorithm that reduces the problem of computing the reduced to echelon form to the problem of solving ax equal to b, which you can solve. There's a really surprisingly powerful method to solve ax equal to b over the integers, which is, again, you solve it mod p. So you just take the problem and view everything here, view all the entries as numbers modulo a prime. And then you just solve this problem there. There you don't have any coefficient explosion. Your prime is really small, so all the arithmetic involves machine size integers. You can do all kinds of tricks, and it's really, really fast. So what you do is you solve the mod of prime, and then you take the answer you get, and you write down another system and solve that mod of prime. You combine that information, and it gives you the solution mod p squared. And then you iterate that process, and each time you solve, you get mod p squared, mod p cubed, mod p to the 4th, and so on. And eventually, you'll get the x modulo a sufficiently large power of p that you can write it down exactly over the rational numbers. There's an extraordinarily good implementation of this algorithm in a library called IML, which stands for Integer Matrix Library, which is included in Sage. And it's a very, very good implementation. Instead of using just one prime, it uses multiple primes, and it does some sort of balanced lifting technique. And it is by far the fastest implementation of that algorithm there is in the world. It's really, really amazing. Although there's different ranges of sizes. So in Linbox, another library in Sage, for certain sizes of the input, that's actually a little bit faster than IML. But the guys that wrote IML are the same people writing Linbox, so it's just, but it's actually much better than the Magma implementation of the same thing. So it's an extraordinarily powerful thing. Basically, if you want to create an echelon form and the matrix isn't too wide, then you can reduce to this solving and it's very fast. And if you want to solve AX equal to B over the rational numbers, this p-adic lifting method that's implemented in IML, which was a master's thesis of a student at Waterloo, is extraordinarily good. Very, very, very fast. And that algorithm is exactly the sort of thing you won't find at all in Mathematica or Maple. Or actually anything except Sage and Magma. I mean, the idea is pretty old. It's called originally it's called Dixon's p-adic lifting method. It goes back, like decades. But it's the refinements and really figuring out how to do it right that makes a big difference. Let's see, I'm finished. So just want to mention that there's some stuff about determinants and characteristic polynomials. Just look at the worksheet online, okay? And we'll start on Friday talking about linear algebra rather than matrix algebra. So vector spaces, intersecting subspaces, that sort of thing. Kernels of matrices.